No idea? Because they're shellfish. Okay, why are mountains so funny? Because they're hilarious. Right? So whoever said, can we get a joke? It was her fault. And it gave chance for 2 more people to turn up, so that's good. Didn't mean to hit that. Oh, good morning, everyone. Good afternoon. We are working on 8.2 today. My goal is to finish 8.2 today, so hopefully we will. We're finding these guys called surface of revolution. And this is the guy that we used yesterday. Essentially what this does is it finds the surface area of a rotated surface when you're given a function y equals f of x and you rotate it about the x-axis. And when you do that, the formula is the integral from a to b, all of this. Now what I've got over here are the other possible combinations. So let me move this to here and talk about the top one, because that's the one I'm going to do my first question on. Suppose you want to take a curve, y equals f of x, but not rotate it about the x-axis, but rotate it about the y-axis. Right, so it's, y equals x cubed, but it's going to get rotated about the y-axis. So you can imagine that shape would be different, and so its surface area would be different. And how do you get its formula? Well, not an awful lot of difference. Do you see the only difference is an x instead of an f in x? You see that? 2 pi x instead of 2 pi f of x. So the math that we do, right, the algebra and the integrations that we end up are not going to be much different in any of these. So the question that looks like this one, I'll put a little 6 on it to remind you, is the curve is 1/4 x squared, take away 1/2 log x, and it's still x from 2 to 3, but the major difference is that you're going to rotate it about the y-axis. So you need to read the question carefully. Is this an f of x question? And which axis is it rotating about? And in this case then, the formula that gets you the surface area is the integral from a to b, 2 pi x, the square root of 1 plus the derivative of this guy squared. Now, if you differentiate up 1/4 x squared, you get 1/2 x. And if you differentiate a log, don't you get 1 over x? So if you differentiate -1/2 log x, you get that fella. So far, so good. I'm going to do this thing here over at the side because there's a lot of bits going on. So let's just focus on what this might look like if you squared it. So it's going to be another one of those foils. When 1/2 x times itself is 1/4 x squared. That's the f done. 1/2 x is this guy times -1 over 2x. Do you know that the x's cancel and you get -1/4? The inside one, you get -1/4, and this guy times this guy is positive 1 over 4x squared. And that's 1/4 x squared, take away 1/2, plus 1 over 4x squared. And then I'm going to add 1. And I get 1/4 x squared, add 1/2, plus 1/4 x to -2. I've decided to call it, instead of 1 over x squared, I'm calling it that. Now this guy here, isn't this guy here going to end up inside the square root? It's got 3 bits to it. What does that tend to indicate?
Perfect square.
And it is. Now remember how the perfect square works. First guy goes here, right? Last guy tells you what goes here. Don't care about the middle. That will get me a half x, right? Plus, and this will get me 1/2. What power of x will I get out of the term at the end here? What will that generate?
One over 2x.
Oh, well done. Or just x to -1 will do, but what you said is better. So it's going to be integral from 2 to 3, 2 pi x, the square root of this guy squared. So 1/2 x plus 1 over 2x, because that's the same thing, squared. But squaring square roots is good. I'll stick my 2 pi out there because they essentially cancel out. And what I would do next is I would distribute the x. So x times this guy is a half x squared. And be a bit careful. What will x times this weird fraction get you?
One-half.
Yeah. So at the end of the day, isn't that integral actually quite an easy integral to find? Isn't it just a power rule? So I'm just going to go dot, 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 and you can finish that yourself. So whatever that comes out to be, 42 pi or whatever it is, 7/11 pi, that would be the surface area that you would get if you rotated this shape about the y-axis. Are we comfortable about the adapted formula to take into account rotating about the y-axis? You just change the f of x at the beginning to an x. Any questions about that, or are we comfortable with the process? Okay, I nod. I like nods. So let's see if I can find one. They're hard to find when you don't want them. I'm going to look at rotating an x equals g of y, right? Like an x equals y cubed plus 1, right? That kind of curve. And it's going to be rotated about the x-axis. And when it is, this is the formula that I'm going to use. So as I scan through here, what do I want here about the x-axis? Here we go. The guy that I found, question 10. And I just noticed something which was kind of annoying, but nonetheless, we'll figure it out. This isn't quite x equals a function of y. Oh, and by the way, this is about the x-axis. So I know I'm going to be using this formula. I just have to figure out where the information comes from. Are you happy with what I did to get x equals? Good? And I need to know that, don't I? Here's something that's not so obvious. They're telling me x is 0 to 13. I don't care what x is equal to. Don't I need to know what y is equal to? How am I going to take x is 8 and figure out what y is going to be?
Plug 8 in for x and solve for y.
Okay, so that's 32. Well, I guess I should do that at the side. So this is the relationship between x and y. I know that at one extreme it's 8, so 4 lots of 8 give me oops. That's a bit ugly, but it gives me a y value of root 12. Now, if I plug in 13 and I do a similar kind of calculation, 4 lots of 13 are 52. That gets me 32. And there's my second guy. So what do I now know is that it's between the square root of 12 and the square root of 32. Are we happy where those two ugly numbers came from? Okay. I wish they hadn't done that. It's a distraction rather than a help. Okay, we got a formula. It's this guy here. The surface area is going to be the integral from the square root of 12 to the square root of 32, 2 pi y times 1 plus the derivative of this guy squared dy. Okay, if you differentiate this guy, you get 1/2 y. No, you get 1/2 y. That was kind of easy. I was expecting more. So from here to here, 2 pi y, the square root of 1 plus 1/4 y squared dy. Where am I going next? I need a technique for integrating this. I should have probably pulled out my 2 pi, but it's too late now. What you gonna do?
Would use substitution rule?
It would. And what u sub would you use?
The 1 plus 1/4 y squared.
Agreed. So you differentiate with respect to y, and you get 1/2 y. You do the crossover, and you get 1/2 y dy. And then you isolate. It's a little bit messy, this, because the half thing. If it was 2y, wouldn't you get 1/2y dy? But it's 1/2 y, so you get 2/y. Are you happy about where the 2 ends up? Because a half in the bottom is really the same as 2 on the top. So I now have 2, oops, not 2 pi. I now have y, the square root of u, times 2/y du. As you'd expect, the y's cancel. I might as well bring that 2 out. I now have 4 pi, the square root of u. Turn it into u to the half. We must have done tons of square roots by now, haven't we? I don't know how many times this has happened. A lot. Add 1 to the power. Divide by 3/2 is the same as multiplying by 2/3, so you're going to get 8/3 pi because of that. 8/3 pi this guy cubed, 8/3 pi, the square root of 1 plus 1/4 y squared, cubed, evaluated at y equals root 12 and at y equals the square root of 32. That's going to get me 8/3 pi. Plug in the square root of 32. Well, square root of 32 squared is 32. 1/4 of 32 is 8. 1 plus 8 is 9, so you get the square root of 9 cubed. Take away. Plug in root 12. Root 12 squared is 12. 1/4 of 12 is 3. Oh, isn't that nice? You see how nice those numbers came out? That's basically 3. 3 cubed is 27. So I have 8/3 pi times 27. Take away 8/3 pi times 8. So let's see what that comes out to be. 8 times 27. Take away 8 times 8. And I get 152/3 pi. So if you take a curve that's x equals, if you take a curve x equals a function of y and you rotate it about the x-axis, this is the formula and here's the working. It's just like all the others, isn't it? They just take forever and a day to do. But at least there's a formula and there's a process. So at least we have that. Those are pretty much, what have I not done? I've not done this one here, right? So let's find an example of a function x equals, a function of y that is being rotated about the y-axis. And the one that does this is question 16. And we have x equals the square root of y take away y squared. And we're being asked to rotate it about the y-axis. And I got an email from someone to do an earlier question where they didn't tell you the start and finish x values, and they ended up being 0 to 1, and the person was saying, how did that happen? Well, here's another example of it. Do you know in this question, they're not telling you y is between 0 and 10 or 1 and 40, and you think, well, how do I do that question? If you plug this guy into a calculator, you will find that the curve only exists in a very small range. Would you agree that a square root needs a positive number inside it? And can you trust me that y minus y squared, if I just did y minus y squared, but I pretended it was x, you know it would look like that? That would be the only part. Actually, in this question, it would look like that, right? So if you plugged it into GeoBra, you could see that it started at 0 and it finished at 1, right?
So that would be something that Desmos would be.
Yeah, you'd plug it into Desmos and look at it, right? And you'd see, the whole thing, right? Plug the whole thing into Desmos and you would see it. So if they don't give you a start and finish value, I'm pretty much sure it's because the curve only exists in a certain place. So if you do a Desmos on it, if there is a verb called Desmos on it, it'll tell you what the range is. So we're cool with that guy? Now, if you're doing a y-axis, the equation for the surface area is the integral from 0 to 1, 2 pi g of y, which is essentially this guy, times, this is why you shouldn't do things without planning ahead. 1 plus, I'm just going to call it the derivative of y squared right now, dy. Right, so once I know what this is, don't I plug it in here and I'm good to go? Agreed? So, g of y is the square root of y minus y squared. Agreed? That's what g of y is, the square root of y minus y squared. Oh. Its derivative. Okay, you've got your differentiation hat on here. Isn't this a messy chain rule? Right. So let's see what you get. You multiply by the power and you reduce the power by 1. But don't you also have to differentiate y minus y squared? Are you happy about where the 1 minus 2y is coming from? Chain rule. Now, I want to make this guy a little bit prettier. So how about 1 minus 2y on the top and 2 lots of y minus y squared on the bottom? Are you comfortable with the algebra that I did on that line? How this became that? Now, what we're going to do, we're going to square it. And add 1. So it's going to be 1 plus, right? If you square this, you square the top, you square the 2, and you square a square root. Are you still with me? We've done this at least twice before. Didn't we have to do style points? These have to be combined. So I'm going to have to call 1 minus 2y squared squared. No, sorry, I'm going to have to call it 4 lots of y minus y squared over 4 lots of y minus y squared plus 1 minus 2y squared over 4 lots of y take away y squared. That means they now share a common denominator. Distribute, distribute. Foil that guy out. And guess what? It's almost like a miracle. Would you believe what's just happened? Dead? Dead. I mean, doesn't that look remarkably nice compared to what it started as? So our answer is the integral from 0 to 1, 2 pi, y take away y squared times the square root of 1 over 4 lots of y take away y squared. dy. Do you like it? Now, here's some interesting news. They don't want you in question 16 to finish the question. They only want you to get it to the place that looks something like that. I want to make it just a little bit prettier. Is there anything you can do with y minus y squared that might make it look a little bit prettier?
Pull out the y.
Yeah, I'm not even sure why they bothered to do that, but that's what they did. And you have got 5 choices, I think, and one of them's that guy, and that's the one you pick. Actually, this question's pretty much ready to go, because can't you cancel this guy with this guy and you just end up with a nice fraction? I'm surprised they didn't just go the whole way, but they didn't. Are we good? Any issues with that question, with all the bits and pieces that it had? I guess I could have done it there, right? In which case it would have went straight in here. Last chance, if there is no questions. I'm going to call this one done. So you want to find a surface area. There are 4 formulas. I would suggest that you make sure that you have each one of them in a, either a separate card or one card with all of them in, so that when you come to do the surface area question, you've got your 4 formula and you know for what particular circumstance each of these formulas gets used. So, final summary. If your function is y equals f of x and you're rotating about the x-axis, use this one. If your function is y equals f of x and you're rotating about the y-axis, use this one. If your function is x equals a function of y and you rotate it about the x-axis, use this formula. And lastly, if it is x equals a function of y and you're rotating it about the y-axis, you use this formula. And if you had all 4 formulas side by side, aren't they very, very similar looking? Right? They have virtually the same kind of pieces. Maybe there's x's where y's used to go or y's where x's used to go, but pretty much the same formula. That went smooth, which is scary. I guess you'll find out when you do the homework and it takes you half an hour each. Okay, I'm moving on then. We have one last section to worry about. We're going to start today and finish tomorrow. See if I can pull it up quickly. Nope, it's not that one. Try again. Gotcha. And ooh, I forgot about this one. Okay, let's see. I'm not quite sure what screen I'm on. Oh, we're on the white screen. Okay, that's good. Now, not everyone here is going to be an engineer, but we're going to show you integration and how it can be used in applications, right, in engineering. How you can use calculus to help you with your engineering classes. So, first topic we're going to look at is called the center of mass. Anybody heard that term, center of mass? Right. So, I want you to imagine that we have a piece of wood that is so thin that its weight is negligible. Doesn't really matter, right? And that this piece of wood has like a ruler, right? Looks like that. And on this piece of wood, we are going to place some weights. And we'll make the weights pounds, keep the Americans happy. At this point here, I've got a weight and it weighs 10 pounds. At this point here, I have a weight and it weighs £5. And this one here, we have another weight and it weighs £15. So what we are looking for in the center of mass, which is very often called X bar, is where on this scale would you put, it's called a fulcrum, a little triangle, like a seesaw, so that it would be balanced, right? So that the forces on one side would be equally balanced by the forces on the other. Now, if you are a gambling person, you might think that it's going to be right there at 0. Do you think it's more likely to be maybe at 1 or maybe at least to the right of 0? Does that seem more reasonable?
Yes.
Right. Now, you can't guess. Guessing is bad, right? So we need to have a way of finding it, right? So this is how you go about finding the center of mass. X bar is going to be where on this ruler you put the little fulcrum thing. So the first thing you calculate is the total mass. In this case, it's £10, add £5, add £15, and the answer I get is £30. The next thing we're going to calculate is called the moments. At least that's what we call it. Do you use the word moments in engineering? Have you used moments? No, well, we'll call it moments. You may have your own name for it. Now I'm going to enter in some notation here so we can keep it general. This position is going to be called X1, and this mass is going to be called M1. And this is going to be position X2, and this is going to be mass M2. And this one is going to be position 3, and this is going to be mass 3. So when I calculated the mass, didn't I really just add up M1 plus M2 plus M3? We're happy with that? Now, to get the moments, you multiply the mass by its position. And you do it for all of the masses. So in this question, 10 times -2, right? The mass is 10, but its position is -2. In this one here, the mass is 5 and the position is 1. And this one at the end, the mass is 15 and the position is 3. This gets me -20. This gets me 5. And this gets me 45. I believe. And what do I get? Oh, 50. I believe I get 30. You know what my accountant's like? Does that look good?
Yeah.
Right. So the center of mass X bar is the moments divided by the total mass. So basically you just divide those guys. 30 divided by 30. So exactly there. So if you wanted to balance this, imagine it looked like this. At position X equals 1, you'd put your little triangle thing, and this guy would balance that guy. Now you might say, oh, at this side here, at position 3, you've got 15. And at this side here, away over at -2, you've got 10. So how come a 15 can balance a 10? Well, have you noticed that the 15 is nearer and the 10 is further away? Do you see that had an effect? What about the poor £5? Isn't the £5 over the centre of mass, so it really doesn't matter in this particular question? So if you wanted to know where the centre of mass of this particular combination of weights is, it would be right there. Okay, let's find a reason for why I want to do this. Can you imagine this is a girder? And on this girder, there's a big heavy girder, there's a little bit less girder, and there's a really massive girder. If I wanted to support this, isn't it best to have it at the center of mass position, because that's its most stable place. So if you're into construction, you want to know where the center of mass of something is, because that's a very important balance point for you to put girders or support beams, right? You know, when they build houses and you watch these shows where they knock things down, don't they sometimes have to put pillars and things? And you wonder, I wonder why they put it here and not there. There's a very good chance that that's the center of mass of that particular, beam that's going across. And you want to support it as best you can at the center of mass position, right? That's the best place to reduce all the stress that a construction would go on. Changing the subject slightly, a lot of you are Navy people. That's an aircraft carrier. Did you know that? I'm good at drawing. Where should the center of mass be for any ship, including an aircraft carrier, to have the most stable boat or ship or aircraft carrier? Where do you want it? Any takers?
I was a submarine guy, but I would imagine the center line, the hull, along the center line of the hull.
You
Yeah,
want
you
it in the center, and you want it as low down as you can get it. Right, why do you want it in the center? Well, see if the center of mass is too far forward, won't the ship dig into the sea as it's traveling? Right, it's an inefficient situation. If the center of mass is towards the rear of the ship, won't you have the opposite effect of the front of the ship coming up a lot? Again, quite unstable for aircraft carriers. For submarines, of course, there's my submarine, you still want it to be in the center, unless you want to dive or go up. And don't submarines and aircraft carriers, don't they move water, I think it's water, from ballast to one place to another? And why are they doing that? They're moving the center of mass around for whatever reason, right? So a fully loaded aircraft carrier is not going to be quite the same as an empty aircraft carrier, right? So they know enough about it. Well, where do these calculations come from? They come from massive versions of these things, right? So it's important, right? Center of mass. Okay, let's try one out. I'll leave this guy here for you. Here is a simple center of mass story. Take me a few moments to set it up. Oops, 0. It's going to be a weight here. I'll make it kilograms. 10 kilograms, 4 kilograms, 6 kilograms, 50 kilograms. Find the center of mass of that situation. "30 seconds, no rush, no pressure."
Uh, 16/35.
Ooh, we have an answer, do we? Okay, let's go for it.
Like I did it real quick. It was like I was trying to be first, so I did it real sloppy.
Well, it sounds like me. So 10, add 4, add 6, add 50. So 50, 60, I make that right now, I make that 70. Does that look good, guys? Right. Now the moments are going to be M1x1, M2x2, M3x3, and finally M4x4. What that basically means is you multiply these together. So what's that going to be? 10 times -5, add 4 times -3, add 6 times -1, add 50 times 2, and that's -50, -12, -6, plus 100. Well, it's going to be 62. I make that 68. I make that positive 32. I get a nod. So what you get the moments over the total mass. And the moments are 32, and the total mass is 70, and 16/35. It's quite close to a half. It'd be roughly about here. Why do you think it's so far to the right?
Because most of the weight is on the right.
Yeah. In that big 50 kilograms, a lot more than all of these weights. Now, if you didn't have this calculation and you were just looking at it in sort of a rule of thumb in it, isn't there a good chance that you probably wouldn't pick that point? You know, visually, you might have picked something, I think most people anyway, would probably pick something a little bit further to the left. Just because there's more things to the left. But it's not really things that matter, isn't it? The weight of the things that really matter. So far, so good? Comfortable with that? Doesn't look like calculus, you're right, it isn't yet, but it will eventually become calculus tomorrow. Let's do center of mass in 2 dimensions. This will be the last thing for today. And imagine that we have an object at this position and it weighs 10 pounds. We have one here and it weighs 5 pounds. And we have one down here and it weighs 15 pounds. So the center of mass here is some point in 2D space, right? Some point in 2-dimensional space that would be, you know, can you imagine if you, no, that's probably a bad choice now because they're all in a straight line. Okay, let me put another one in up here worth 5 pounds. Can you imagine a triangle with weights placed on it? If you were a guessing or a betting person, would you might think somewhere in there might be the center of mass? Well, don't be surprised if it's not. First thing you get is the total mass. So we're going to extend this idea. In this case, it's 15, add 5, add 5, add 10. And that's 35 pounds. Here's the difference. The center of mass is now an X and a Y. We agree the center of mass is a 2-dimensional position. So to get these guys, we have to do 2 separate calculations. If I cover that up, isn't that essentially what we do all the time? Now, what do I mean by X1, Y1? every single one of these 4 points, don't they have an x coordinate and a y coordinate? So when I say M1, X1, let's call this guy X1, let's call this guy X2, let's call this X3, right? Call this guy X4. I'm talking about the x coordinate of each of these points. Right, what's this guy going to be? Well, he's going to be 15 times his x coordinate, which is -1. What's this one going to be? Well, his x coordinate is 2, and so it's 5 times 2. What's this one going to be? Its x coordinate is 3, so it's 10 times 3. And this last one that I put in as a kind of last minute is £5, and its x coordinate is 1. And that whole thing gets divided by 35. So what's that? -15, add 10, add 30, add 5 out of 35. That's going to get me 10, 20, 50. 50 out of 35, 25 sevenths. It's about 3 and a bit. It's about roughly 3.5, very roughly. Let's get y bar. It's going to be M1, Y1, M2, Y2, M3, Y3, and finally M4, Y4. And it's also going to be divided by the total mass. Okay, this is the first point. Its y coordinate, its mass is what, 15, and its y coordinate is -1. This one has a mass of 5 and its y coordinate is 0. This one has a mass of 10 and its y coordinate is 1. And this guy up here has a mass of 5 and its y coordinate is 2. All divided by the total mass. -15, 0, 10, and 10 out of 35. This answer is -5, no, sorry, +5 out of 35. It's 1/7. Oh, so 25 sevenths, comma 1/7. Let's see where that would be.